Hello everybody, if you still find difficulty in chemistry paper 1, this is the right video, do not scroll by it. Now, if you are still confused of the topics or what to revise in chemistry, it is high time you strategize. It is high time you strategize. So, first and foremost, you should know what is coming. You should know that item 1 consists of this, item 2 consists of this, item 3 consists of this. I am ready for this and this and that. That is called a prepared student. You are left with not more than 2 months. Did you know that? Not more than 2 months. So let us strategize right now. Schedule yourself. By this week you're done with this section, by this week you're done with this section. Reaching this month is done, you are all ready, and next month you're just practicing papers on papers. So that is the spirit, guys. Now, assessment objective 1, assessment objective 2, obviously, organic 1, organic 2, organic 3, you need to be good at that. Basis of the assessment, from there you need to be good at explained properties. Explained properties, mechanisms, not direct, they usually give you them indirect. So you should be able to describe mechanisms. You should be able to talk about, to write those formulas of the mechanisms, write properly, elements, write them properly. You know the rules of mechanism. Synthesis, a good UNEP synthesis is running from usually the steps of 1 to 6. However, if it's above, it's okay. However, a good professional looking one, it is in the range of 3 to 6. But I'm not saying less or more is not okay. Are we together? Then the last one from that assessment, basis of assessment of their objective 2, it is explained application, dangers and mitigations, usually 2 to each of them. We should give applications, 2, dangers, 2, mitigation, 2, explain them properly. Yeah. In organic chemistry, all of you should be by now done with alkane, alkene, alkyne, aromatic, alkyl halide, alcohols, carbonyl, carboxylic, ester, amines. Applied organic usually talk more of polymerization. Those of soap, bichi, no, it's not much required. However, look more of polymerization, unless your teacher says so. Are we together? So that is a hidden trick about that. So, assessment objective 3, we look at thermochemistry, chemical kinetics, electrochemistry. Basis of assessment in this assessment objective 3 is ability to explain factors, theory, principle, laws properly. Explain them. Are we together? Yeah, of course, you can't have principle and law at the same time. It is either principle or law, or it is a theory. Are we together? So, yeah, those are obvious terms you should be able to talk of. For example, factors of, so you should be able to explain them. Theories, explain them. Principles, explain them. Laws, explain them. Some of them perhaps would need what? Formulas. For example, laws. Most of them are calculated formulae, not wordy. Are we together? Yeah. Then another basis of assessment, analysis and interpretation of data, usually by calculation or graphically, and then you conclude it. Then another one is concept plus application and recommendation. All of that you should be able to talk of. Then let's look at assessment objective 4, usually from the topic of equilibrium 1, which is chemical equilibrium and ionic equilibrium, equilibrium 2, which is physical equilibrium, and colligative. Lastly, moles and equation. They have transferred this in assessment objective 4. Basis of assessment in this objective 4 is factors, law, principle, theory, as I said so, well explained. Analysis and interpretation of data, usually by calculation or graphically, and then you conclude it. Explained application, usually give roughly 2 of them. Now let's look at the beauty of this. We are starting direct with listen to me, all the graphics, all the graphs in physical chemistry, they lie in this book that I'm just going to talk about. Now, We're going to use the same. Now we're going to use the same. Now the point is, I've summarized all the graphs here for physical chemistry. So first and foremost, we're going to start with colligative properties. In colligative properties, the first graph, but before that, a good graph must be containing a T per C. A T per C, when I talk of a T per C, a title, plotting, axis, scale, shape of the graph, whether it is contains a line of a best fit or it is containing a curve. Are we together? So, and some of them do not have a good shape. For example, a graph where the points are down, some are up, the points look disorganized. You have to not be like too strict and make sure the curve passes by each of the points. So some of the points are ignored to make your curve shapeful, not shapeless, like So that is how it is done. Now, you have known now what graphs are supposed to contain. Let's start with colligative property graphs. The first graph is a graph of freezing point against concentration. As you have seen, when you're getting the slope is got by negative Kf of the molar mass. This point that you see is a freezing point of a pure solvent, the one which has been extrapolated up there. That is the point. But however, if this concentration of mine is not 1,000 grams per decimeter cubed, we're going to get our slope to be negative 1,000 Kf out of 250 molar mass. Are we together? That is how it is done. Then, when we get, again in colligative, our graph of depression of the freezing point, again is the concentration, it is a positive slope. Are we together? In which our slope is going to be Kf of out of the molar mass. However, at the same time, if my slope is not 1,000, if my concentration is not 1,000 grams per decimeter cubed, what I'm going to do is, I'm going to get my graph, not negative, this is already a positive slope, I'm going to get it by slope is equals to positive 1,000, or it is slope is equals to 1,000 Kf over 250 molar mass. That is how you're going to do. And at the same time, if in colligative I get my graph of osmotic pressure, again as a concentration, I'm going to get a positive slope, in which my positive slope is going to be generated by RT, in which my R is a gas constant, RT of the molar mass. If in case my concentration is not 1,000 grams per decimeter cubed, what I'm going to do is, I'm going to say a slope is going to be got by 1,000 RT over 250 molar mass. And that is all for the graphs in colligative properties. Let us dive into chemical kinetics. In chemical kinetics, when you talk of the graphs, there are usually two. The graphs of zero order, the graphs of first order. There is no graph of second order. Are we together? However, there is a graph of activation energy that is done only practically, in practicals, not theory. Now, when you talk of the graphs of zero order and first order in theory, they consist of determination of two things. One, half-life. Two, decay constant. Are we together? Now, when we talk of graphs of zero order, they are used usually in determination of decay constant. Now, when we have the first graph, it is the graph of concentration against time. We are going to get our slope, which is negative, going downwards here, in which we are going to obtain our slope by getting negative k. That is it, negative k, and that is how you are going to obtain your slope. However, if my slope is of log of the concentration of against time, I'm going to get my slope to be negative k over 2.303. That is how it is done. Negative, of course, because it's a negative slope, as you have seen here. However, if I'm getting my first order, in my first order, you should know that if you are getting your lean of the concentration of again, it's time graph, you are going to get a negative slope in which my slope is going to be got by negative k. Are we together? Now, as you're seeing here, this one is here x naught. At point where this graph has been extrapolated here, it's x naught. This x naught helps to get osmotic, it helps to get original concentration when time is 0. Are we together? That one there, that point there, as you're seeing, where this one has been extrapolated. So you should be able to note this. However, at the same time, another dangerous graph is here, which is rare but dangerous. You should be aware of it. That is the graph of concentration against time, in which my n naught is here. I'm going to get a curve, not a line, a curve, as you have seen here. My n naught, when it is here over 2, when I'm going to extrapolate to get the time at which this decay has taken place, it is going to move downwards. You see how the thing is good graphically? That time t is when a half of this n naught has decayed. And then when my n naught of the 4, I want to get the time, I'm just going to extrapolate it to get the time. And that is how it is done. Now to get the half-life, I'm going to get it by ln 2 of k or ln 2 of lambda. That is how to get the half-life. Now, in case my time 1 and time 1 is approximately to time 2, that becomes the first order. And that is how the journey is done. Lastly, let us look at activation energy. Activation energy, it is done practically. Are we together? It's a graph of temperature effect graph. It's a temperature effect graph. Pardon the way how I've drawn, but it's not a positive slope. It's a negative slope. Are we together? This one was a mistake. It is a negative slope, in which it's going to be a plot of ln k against temperature, which is 1 out of t. A graph of ln k against 1 out of t, which is the temperature. And my slope is going to be good by negative Ea out of r. In case my graph is of log, so it is going to be plotted log k against 1 over t. Of course, again, it's going to be a negative slope, in which my slope is going to be negative Ea, activation energy, over 2.303 r. And that is how the things are going to be quantitated. Now, lastly, the graphs in physical chemistry originates from steam distillation. Are we together? Steam distillation. Graphs of steam distillation contains only lines of base fit. Contains lines of base fit. Now, of course, when you look at this, is just a summary, okay? It's not a perfect drawing. When you get your graph, you're going to plot your first line, which is for the volatile compound. You're going to plot the second line, which is for the water. You're going to plot your second, and in the third line, which is for the total vapor pressure. For example, if my PT for the total pressure is here, my P water is here, my PX of the volatile is here, and remember, it is a graph of Vp out of temperature, vapor pressure against temperature. Are we together? And that is how it is done. If my highest temperature is there, to look for the highest temperature, I'm going to get my here plot it to originate down there to note what is there. I'm sure you guys have learned this. Or pardon the way I've drawn this, supposed to be like this one here, such that this could be approximated to it. However, that is it. Now, and that is how you're going to draw it. That is it. You guys are all aware. You have learned the theory part of this thing. So that is how it is. So if you're to get this temperature, this is the temperature of the mixture, in steam distillation. That is how the journey is done. Lastly, the graphs of Kd. Kd. The graphs of Kd, obviously, it's a graph of concentration of A of the organic against concentration of A of the aqueous. You're going to get a positive slope, in which my slope is of Kd. A slope equals to Kd. So that is how the things are done here. Then in conclusion, the graphs of eutectic, pardon the spellings, eutectic graphs, eutectic graphs. Some people pronounce this eutectic, however. Now, eutectic graphs, it is quite tricky, but the first and foremost, what is eutectic mixture? Can someone define for me that? What is eutectic mixture? Someone define for me that, please. Now, when you're getting your graphs of the eutectic mixture, usually we have our composition of the tin, we have our melting point of the tin, we have our melting point of the lead. Lead is right there. Now this line that you're seeing here is the eutectic temperature. And the point you're seeing right here is the eutectic point. Are we together? What is right here in this space is a liquid mixture, and what is right here next to the lead is a solid lead plus a liquid mixture, and what you're seeing right here, this space here next to the melting point of the tin, it is what? Solid tin and liquid mixture, and that is it. Now, the question, and what is here in this space is it? Solid tin and solid lead. Now the question is, when we look at the description of the temperatures, which is 85 degrees Celsius, and you are to describe for me this, put for me, how do you think you're going to describe this that I've just shown for you? Goes downwards there. And those are all the graphs in physical chemistry you should know of. First and foremost, we started with the graphs of colligative properties, we went to the graphs of the chemical kinetics, we went to it again, we took to the graphs of steam distillation, and we went to KD, and we concluded with the eutectic graphs. All of them are the graphs needed. You have to have them with you. Physical chemistry graphs, tell it 100% tick if you have all of this with you.